Hey everyone, and welcome. So, that big metallurgy question on your exam, question 7, if it's got you feeling a little bit stressed, don't worry. You are in exactly the right place. Today, we're going to crack it wide open by following the incredible journey of one of the world's most important metals, aluminum. Let's get right into it. So, here's our game plan for today. We're going to start right at the beginning, from the rock itself. Then we'll cover how we purify it using Bayer's process. After that, it's time for the main event, the electric meltdown, the Hall-Héroult process. We'll peek inside the chemical reaction, see what's really going on. Then we'll talk alloys, making aluminum stronger, lighter, and faster. And finally, we'll wrap it all up with your ultimate exam game plan.
All right, first things first, where does this all even come from? Every great story has a beginning, and for aluminum, that story begins deep in the Earth's crust with one very specific type of rock. This is ground zero for our whole process.
And that brings us to one of the most basic, most common questions you are guaranteed to see. What do we call the common ore of aluminum? Come on, you probably know this one. It's right on the tip of your tongue. That's it. Bauxite. And don't just memorize the name. That chemical formula is just as critical. Al2O3 dot 2H2O. All that means is it's aluminum oxide that's hydrated. It's got a couple of water molecules attached to it. Seriously, know both the name and the formula. These are easy points you just can't afford to lose. Okay, so we've got our bauxite, but when you dig something out of the ground, it's not exactly pure, right? It's messy. It's got all this other gunk mixed in, impurities like ferric oxide and sand. So our next job is to clean it up. And for that, we use a very clever method called the Bayer's process. This leads us straight to another absolute classic exam question. They love to ask this. In the Bayer's process, we use a specific chemical, sodium hydroxide, NaOH. Why? What is its special job? Okay, so here's the genius of it. The sodium hydroxide acts like a chemical magnet, but only for the stuff we want. It dissolves the aluminum oxide, turning it into something called soluble sodium metaaluminite. Now here's the cool part. All those impurities, the sand and the iron oxides, they don't dissolve. They get left behind as this thick sludge called red mud. Then we can just filter it all out. This process, by the way, is a hot tip for the 2026 exam, so make sure you understand this part inside and out. So now we have a pure white powder called alumina. We're getting closer. But we need to get the metal out of that powder. And to do that, we're going to need a whole lot of electricity. This is where things get really electrifying, literally, in what's known as the Hall-Héroult process.
But wait a second. You might be thinking, why all the drama? We've got the pure stuff, the alumina. Why don't we just melt it? Just heat it up till it's liquid and then zap it with electricity. Seems way simpler, right? Well, there is one massive, and I mean massive problem with that idea.
And this is the problem. Yeah, you're seeing that right. The melting point of pure alumina is over 2,000 degrees Celsius. That is ridiculously hot. Trying to keep a giant factory at that temperature would be unbelievably expensive. The power bill alone would be insane. It's just not practical. And this is where the true genius of Hall-Héroult comes in. Instead of trying to melt the alumina by itself, they figured out you can dissolve it in a molten mixture of two other chemicals, cryolite and fluorspar. Think of these as chemical shortcuts. They act as a flux, which is just a fancy way of saying they help something else melt at a much lower temperature. And look at that drop, from over 2,000 degrees all the way down to a much more manageable 950. That single trick is what makes producing aluminum affordable. Okay, let's pop the hood and look inside at the electrolysis itself. This is where the magic really happens, where electricity rips the aluminium apart from the oxygen. And to get it, you have to understand the two main players in this game, the cathode and the anode. You'll often see a statement like this in an exam question. It's not just a random fact, it's a huge clue. They're telling you something important about the setup. So if the whole tank is lined with carbon, what role do you think that lining plays? And boom, there's your answer. That carbon lining is the cathode. It's the negative electrode. And this is where our prize is won. The positive aluminium ions, Al3+, are attracted to that negative lining like a magnet. When they get there, they each grab 3 electrons, they become neutral aluminium atoms again, and poof, you've got pure molten aluminium metal pooling at the bottom of the tank, ready to be collected. Okay, so that's the cathode. But what about the other side of the coin, the anodes? These are big carbon blocks that are dipped into the hot liquid, and they're the positive electrode.
And here's another favorite exam topic. These anodes don't last. They have to be replaced constantly. So why? What's happening to them?
Well, it turns out the anode makes the ultimate sacrifice. The oxygen ions that we broke away from the alumina are negatively charged, so they're drawn to the positive anode. But when they get there, they don't just hang out. They violently react with the carbon of the anode itself, forming carbon dioxide gas. This means the anode is literally being burned up or eaten away by the oxygen. It's a sacrificial part of the machine. So, we did it! We've made pure aluminum! But believe it or not, for many high-tech jobs, like building airplanes or race cars, pure aluminum is actually a bit, well, soft. To really unlock its potential, we have to level it up by mixing it with other metals to create alloys. And yes, this is another key topic for the exam. Let's look at the two big ones you absolutely need to know. First, duralumin. You add a little bit of copper, magnesium, and manganese, and suddenly you've created an alloy that is super strong but still incredibly light. Perfect for the body of an aircraft, right? Then you have magnesium, which is mostly just aluminum and magnesium. Same deal, strong, light, and perfect for things like aircraft parts and sensitive scientific instruments. The takeaway here is simple. Alloys are how we tailor-make aluminum for the job. Now, before we get to the final game plan, let's tackle one more thing. It's a predicted focus for 2026, and it's a classic spot for confusion. We've talked about purifying bauxite, but there are other methods for other ores, like roasting and calcination. The difference is super simple but critical. Just remember this. Roasting is for sulfide ores, and you do it in the presence of oxygen. Calcination is for carbonate ores, and you do it in the absence of oxygen. That's the key, with O2 or without O2. Don't mix them up. All right, team, we have done the work. We've followed the entire journey, from a simple rock all the way to a high-tech alloy. Now let's lock it all in and distill it down into a clear, simple battle plan so you can absolutely crush question 7. Here it is, your final checklist. Number 1, master the Bayer's process. Know the flowchart, know the equations, know why we use NaOH. Number 2, memorize the reactions at the cathode and the anode during electrolysis. You should be able to write those out in your sleep. And number 3, nail down that key difference between roasting with oxygen and calcination without oxygen. Focus on these 3 things and you are going to be in amazing shape. And that's our deep dive. We've gone from a humble rock in the ground through a chemical wash and an electric meltdown, all the way to the materials that let us fly. You've seen the whole story. You know the key secrets. So the only real question left is, are you ready to explain it? I think you are. Thanks for joining me.